Hello. In today's lecture, we're gonna switch gear to cover a new topic, which is called unsupervised learning. Okay, so previously we talked about the classification and we talked about the regression, all kinds of tools, support vector machine, regression, logistic regression, neural network, deep learning tools. But for those type of data sets, we always have response variable y, which we call it label. But there is also another class of the machine learning problem that does not have the label y. Okay, so we have sample points. But no labels. Okay, so we don't have the classes that the training data set, we don't have the classes or the y values. Or nothing to predict. So but the goal is we want to discover some other structures in the data set. So the goal of the unsupervised learning, discover structure in the data set. And specifically, there are several tools commonly used for unsupervised learning. For example, clustering. So, which means we partition the data into groups. Based on the similarity or nearby points. Or there is another type of the problem requires the dimensionality reduction. The data often lies on the low dimension subspace in the feature space, and we want the low rank approximation of the huge dimension data. Okay, so dimension reductions. We have the many big number of the features in the data set, but how can we get the smaller lower dimensions of the features, but we still keep the similar amount of the information we have. Okay. Clustering is about grouping the similarity of the points. Dimension reduction is more about the identifying a continuous variations from sample points to sample points. So clustering and dimension reduction is a little bit different. Another type of the unsupervised learning problem can be think as a density estimation. Density estimation. For example, we fit a normal distribution like in previous support vector machines. Gaussian discriminant analysis, we fit the Gaussian distribution to the data first. That density estimation is the result of this analysis. So there's no label for the predictions. So these are the non-purpose for the few examples for the unsupervised learning. And in today's lecture, we're gonna focus on one tool called the principal component analysis. Principal component analysis. And we're gonna give you motivation, and also we're gonna give you the derivations of these methods. It's called a PCA. It's in some areas, like in the biology, in the gene studies, PCA is a unique, important tools that for identifying there are many applications in biostatistics, in gene studies. Okay. The goal of the principal data component analysis is given sample points, we want to find the k dimensions. So suppose you can think this d is a higher, so you can think this d a relative large number. We have the relative large number of the feature space, and we want to find a d. We want to find a k directions. That capture the most variations. That capture the most variation. Okay, so usually this k will be less than d, right? So you have large number of the features, and you want to find you want to use these d features to construct the k new features. Okay, and we have the relative smaller number of the features, but we still keep the same information, which in the sense that we want to capture the most variations in the data. Okay, maybe I can give you a plot. So in this example, we have the 3D features, and by using the principal component analysis, so suppose so this is like so this is the picture, the scatter plot on the left hand side describes the 3D features. You have the in this data set you have the x-axis, you have the y-axis, and you have the z-axis. So each point has the 3 coordinates: x, y, and z. Okay, so the original space d equals to 3, and by the principal data component analysis, we produced another 2 features. So you can think this is a transformations. You can think this is we construct 2 features based on the original 3 features: x, y, and z. X, y, and z. Okay, based on this original data 3 coordinates, we construct 2 new features, and with projection on these 2 new features, we can see there are 3 clusters. There are 3 clusters here, 3 groups of the data, and this is called principal component analysis. And here is another example. Maybe let me show you another example. This is the number of the digits, like a MNIST data set. MNIST data set, which contains all the handwritten images. By using the principal component original data set, remember each picture, for example, each handwritten picture, we cut it 28 to 28 pixels, right? So there are 28, and there are 28 here, and each pixel's ranges values is a number from 0 to 225 something. So in other words, original data space will be 28 times 28. We have the 28 times 28 features, which is multiplied together is 784 dimensions. So in other words, your input is x1 up to x784. So you have in this case, D equals to 784. And by the principal component analysis, we can, using these 784 features, construct much less features. For example, so here we showed the first component and the second component. Okay, so the first component, second component. Okay, and we can say since the digits with the similar numbers, for example, handwritten 0 is more clustered here, and the numbers with ones all clustered here. So we construct new features based on this. So k here is equals to 2. Since we can using only these two new constructed features, we can classify the numbers. Seems doing the reasonable job. Although there are lot of the overlappings, but I think, here we only use the 2 principal components. Although 2 dimensions are not enough to fully separate the digits, but observe that the 0 and 1s, this represents 0, this represents 1, are well separated by this technique. So this is the output of the principal component analysis. And why does this work? Okay, why do we need the principal component analysis? Let me write here. Why do we need PCA? Okay, we want to reduce the numbers of the dimensions of input features. And then make some computation cheaper. Speed up computation. Okay. Another thing is we want to remove irrelevant dimensions. For example, I believe in this MNIST dataset, the most features in the center part matters a lot, but there are also on the corner part of the features won't matter that much because they mostly are zeros. So by doing the principal component analysis, we can throw out the irrelevant features. Like the subset selection of the features, but these new features are linear combinations of the input features, and the new constructed K features are linear combination. A linear combination of input features. Okay. And also, at the end of the lecture, I'm gonna show you some example. Principal component analysis can also be used for the visualization. So, for example, can be used to construct the small basis. For representing variation in complex things. For example, there are many very important application of the principal component analysis is to construct machines for the face recognition. Gene studies. Okay. And there are a lot of cases. That sometimes principal component analysis is used as a pre-process. Before regression. Or classification. For example, a lot of cases, if your regression model you constructed, even you use deep learning models or regression tree models, you cannot reduce your RMSE. So it would be helpful if you can implement the principal component analysis to classify the training data point. So once you find the clusters of your training groups, hidden training groups, and then you apply the regression on each clusters, usually the performance will be better than you apply the regression to the global data set. And in the next video, I'm gonna show you how to how to derive the principal component analysis.